let's try and derive the Leeson equation that gives the minus 20 dB per decade slope of phase noise to carrier ratio for an oscillator. The algebra is quite straightforward really, no more than O-level standard as it was when I did it, and that's GCSE now. I imagine that's about the same level, but you do need to understand a bit about electronics, concepts such as noise, power, spectral density, and how sidebands work, and matching, and these sort of things. But it's not that difficult. Right, these are all the variables used. You can stop the video at any point, of course, to look at it, and it might be worth taking a screenshot of something like this if you want to go back and look at it. This is the block diagram that we're simulating. We've mentioned before, and so we've briefly explained how we're analysing the oscillator. This is not a circuit, it's a block diagram, but the levels here are voltages, not powers, or these factors multiply by voltages. I should also mention that the variable Pin we've used, the input power at the amplifier, I've sort of loosely called it Pin, the input power to the amplifier. Now strictly speaking we should call this the available power. When an amplifier is being noise matched at low levels in receiver type systems, it's not actually the input power that matters, it's the available power. The reason for this is that the amplifier isn't matched for a perfect power transfer. We want to optimize the signal to noise ratio, and the noise depends on the impedance looking back out of the amplifier into the load, and so the match that gives the best signal to noise ratio isn't necessarily the match for best power transfer. So we don't really consider the power going into the amplifier, we consider the power that's available that could go into an optimum load. Now in oscillators things are a bit different actually, more complicated in fact, and even this isn't quite precise. Perhaps we don't need to be too pedantic about how we define this power level at this point. I will mention a bit more about it later. Right, so this is the block diagram, and let's look at how all this works. So first of all, here at the top we have the function of the resonator. It's a fairly normal way of representing a resonator. At center frequency, this imaginary component on the bottom is 0 and the ratio is 1, and then as we go away from center frequency this imaginary component increases, and so the transfer function goes down. Here we have the transfer function of a feedback system, usual sort of thing. So we have the open loop gain divided by 1 plus the gain times the feedback factor, and so if there's no feedback, either positive or negative, we just have the gain, and in the case of positive feedback this gain times feedback must subtract from the 1, so we increase the gain by the positive feedback, and that's what we're doing here in an oscillator. Of course in the negative feedback case this would add to the 1. So if we put the variables in our block diagram we've looked at into this equation here, this is what we get, the output to the noise input ratio of the overall system. And we're looking at this as a narrowband amplifier of noise really. Now we'll just square that function we looked at on the previous page, so this is the output power to noise power ratio. And now here a thing we need to take into account is the ratio of the noise bandwidth to 3 dB bandwidth. When we look at things with normal complex algebra we work in terms of 3 dB bandwidth, and the noise bandwidth is actually slightly wider than 3 dB bandwidth. This ratio depends on the type of filter we have. The higher order the filter, the narrower the noise bandwidth will be, but it's normally always wider than 3 dB bandwidth. In the case of a single simple resonator, this is the sort of ratio we have. Now another variable we need to define is H. This is just for convenience. H is the bottom of the feedback equation at center frequency. So this here is the ratio by which parameters are changed by the feedback. So this is the ratio by which the gain will be changed by feedback, and also the ratio by which the bandwidth will be changed by the feedback. So the oscillator bandwidth is going to be equal to the bandwidth of the resonator multiplied by 1 plus AKF, this factor H. So this is going to narrow the resonator bandwidth. Right, now we can calculate what the noise power is at the input. It's the noise figure of the device times the Boltzmann constant times temperature times the bandwidth of the resonator times this factor for the noise bandwidth to 3 dB bandwidth, and this factor by which the feedback will narrow the bandwidth. Now the output power we're defining as P. That's one of the basic ways we're going to set this thing up. In fact, we've mentioned there's going to be this hypothetical AGC system that will control the power to be this. So we've controlled the gain to get an output power of P, and this is just what we've got above. So we can actually rearrange this equation so that we make 1 plus AKF the on the left hand side here. Now this is very useful because now we have got something in terms of the parameters of the circuit that we know about that defines this ratio by which we're going to change the circuit operation. So now we're starting to get somewhere. We can see how much the bandwidth is going to be narrowed. Now let's just digress a little bit and work out what the peak output power spectral density will be. We're saying that this system is going to take wideband input noise and it's going to filter it by a very narrow function. So this is the function we're going to filter it by. This is the response of the resonator, which has been narrowed by feedback, and this square thing here is the noise bandwidth, the square noise bandwidth, which is equivalent to the bandwidth of the actual system, an equivalent square bandwidth. The peak output power spectral density, this here, must be equal to the output power divided by the bandwidth. So this enables us to get this. So the output of the oscillator, the power spectral density at the output of the oscillator, which we're trying to calculate here, is equal to the peak power spectral density multiplied by this resonance curve. And we know what the resonance curve is. That's the standard resonance of a resonator, and we know how much it's narrowed by. So that's why we need to know what this peak power spectral density is. So the output of the oscillator is equal to the peak output PSD multiplied by FR dash squared, where FR is the resonator function and the dash indicates its been changed by the effect of the feedback. Now let's just simplify the function of the resonator a bit for this purpose. We've just used a simplification here, and I think you should be able to see by inspection that this is an approximation to this. The approximations we're making here is that inside the brackets this term and this term are fairly close to each other at one end of the frequency range, and at the other end of the frequency range that this one is fairly small compared with this term here, and providing those are valid, then this approximation is fairly valid. So here you see, for the example we're going to show at the end, this is the error caused by this approximation. You can see if you go to very low offset frequencies and very high offset frequencies, there's an error, but over the range we're concerned with, the error is small. It just simplifies things. Right, now this is just putting the actual variables in for what we said before. The output noise is equal to the peak output power spectral density multiplied by the resonator function. And now we're going to change from Q dash to Q by multiplying by H squared. Here by Q dash what we mean is not the loaded Q of the resonator, but the loaded Q of the resonator acted upon by feedback. So that's the when the oscillator is running, that's the actual filtering function we have, but really what we need to need to have in terms of an equation that represents the oscillator is the actual loaded Q. So because this here is squared, then to get from Q dash to Q we need to multiply by H squared. So that's what we do down here, and we've also put the P on the bottom. So now we've actually got the noise out of the oscillator to the power ratio, and we've got an expression for it here. Right, we just carry that over to this page, and right, yes, so we've got H here, and we need to put some variables in for H, so we know what H is, and H is 1 plus AKF, which is this. So we put that into the equation, and that gives us this, which simplifies to this. So this is the equation carried across from the previous page, and so here we do have an equation which is a perfectly valid equation we could use, that is giving an expression giving the noise density to power ratio, carrier power ratio, at a specific offset from the carrier. But the thing about it that's not ideal is we've got two things in it which are not directly important. We've got here A is the voltage gain of the amplifier, so this is the power gain of the amplifier, and this is the output power of the oscillator. Well, of course, in Robin's equation the output power of the oscillator was in there, but it was expressed in a different way, so this wasn't here. But in this more general equation we could express it like this, but it's better to express it in this form here, where we've replaced A squared and P by P in. We know that P in, the input power to the oscillator, is the same thing as this, and really P in, the ratio of the noise density at the input to P in, is the thing which determines the noise at the output. So really this is a clearer way to express it. Now this is all of the noise at the output, the noise density. Only half of this is phase noise. Remember, we're just considering all the noise coming through, and half of this will be phase noise. There's no reason to suspect otherwise. It's completely random noise. It's only in relation to the carrier that it becomes phase noise, so half of that's going to be phase noise. In a limiting oscillator, of course, this would be removed anyway by the hardware, but since we're not actually considering the action here in the analysis of it, half of that power needs to be removed. So this is really Leeson's equation as it should be. This is the phase noise, the density of the phase noise at a specific offset from the carrier. Well, I should say it's really actually this whole thing here that is the phase noise, because this is the density of the noise that causes phase noise, and this is the carrier power. So it's only these two together that represent phase. And so what we've got here, the noise figure, Boltzmann constant, temperature, input power to the sustaining amplifier, the loaded Q of the resonator, the offset frequency at which we're specifying the phase noise, and the carrier frequency. So if you plug the variables into here for a specific offset frequency, this here is the phase noise that's predicted. And the units, of course, it's normally presented logarithmically, but here we haven't taken the log of this, so this is watts per hertz on the top and watts on the bottom. So I hope that makes sense. Now, another thing I didn't explain as we went through, I'd just like to show, which can be shown quite easily. When we've got feedback applied, we know that the gain of the system is changed by the factor 1 plus AB. Now, the bandwidth and the Q are also changed by the same factor. If the gain is increased by 10 times, the Q will also be increased by 10 times, and the bandwidth will be reduced by a factor of 10. And we can easily see how that happens. Here we have a simple system, a voltage source, a perfect inductor and perfect capacitor which are resonant, and a resistor. And the output current is of course equal to the voltage divided by this resistor at centre frequency. Now if we put an amplifier in, this is an amplifier which is purposely, a bit of an unusual amplifier, purposely put in here so we can easily see what happens. The input to the amplifier is just two terminals linked together, and the amplifier measures the current going through these terminals and produces a voltage at the output which is proportional to this current. So the amplifier can change the effective value of this resistor by changing the voltage on the end of the resistor. With no current, this voltage is 0. So we can see that the gain will be changed. If we reduce this resistor by a factor of 10, then the gain will be increased by a factor of 10, and we can see that the Q will also be increased by a factor of 10, because the Q is this reactance divided by this, and the bandwidth will of course be reduced by a factor of 10. So I hope that clarifies that. Thank you for watching. In the next video we will make a practical oscillator to show Leeson's equation does work.